Hello everybody and welcome back. Today we're going to be talking about work and potential energy and how to use line integrals and gradients to solve problems. So first of all, let's talk about the idea of work. So work in the context of physics equals force times distance. And in this case, notice that this is a dot product. And so really what this equals is force times distance here. We can just say times distance times cosine of theta. And that's what the dot product means. You attach a cosine because really what this is saying is that these two are vectors. And so the cosine theta is the angle between those two vectors. And so that's perfectly fine for if it's just in one dimension, it's moving in one direction, and distance is easily calculable. But let's say that it isn't, and let's say that you're summing up these infinite tiny distances together. And so what you can do is turn it into a line integral. And this allows you to sort of take it in 3 dimensions, and if you can find the distance of that line, then you can integrate it across that force. So we can say that work also equals the line integral of f times ds. So in this case, s is just that infinitesimal distance. And then also, quickly before we go and try to understand this equation for work, let's take a turn and talk about gradients. So gradients, typically we have this function called nabla. And when you take that of a function, essentially what it does is taking the partial derivative of f with respect to x. Sorry, that should be a partial. And that goes to this I, which is the x component of a vector. And then likewise, we have the partial of f with respect to y of j plus partial f with respect to z of k. And so these little hats essentially represent, like on the I and j and k, they represent that it's a vector and they're components of the same vector. And this actually goes for however many dimensions you want to do it. And what this gives you is the rate of steepest ascent. So how, like what direction can you travel in order to gain the most force or gain the most work? And so if we look at it in the context of a function, what we can say, for example, is, here is the function x squared y squared. And so in this case, the redder the region, the higher the z value, or the higher this f value. So if this was an equation for work, the blue region would represent a lower work value, and the red would represent a higher z value. And so if we were trying to take the gradient of this, what we could say is that the gradient of f would just be the partial of f with respect to x times the I, plus the partial of f with respect to y of the j. And so if we look at this, the partial of this with respect to x, you just consider y to be a constant in this case. So this would be 2x times, so y squared is just a constant, so y squared, and that is for the I component. And then that's going to be plus 2y x squared in the j component. And so if we're to draw what this sort of looks like, it ends up, here we can change the color here, and let's do an orange. And so essentially what this would look like is you have vectors pointing away from the center like this. So this is showing you that if you travel in any direction from the center, it's going to increase. And then you have this sort of almost spiral-like pattern where things kind of move in towards the center here, and they go in this direction and point you towards this highest point down here. So in this case, of course, I'm only showing a discrete number of vectors, but really the entire vector field is actually continuous. And in this case, I'm showing that the magnitude, so the shorter the vector, the less steep of an ascent it is, and the larger the vector, of course, when you get to right here, down to this side over here, these are going to be huge vectors because they're increasing the fastest. It's showing you the steepest ascent there. So then if we're to go back to forces, essentially what we can say, and so what we can say is that this force is conservative. And so what this means is that the work done does not depend on the path taken. So if you're going from point A, to point B, it doesn't depend on the path you take. For example, you really could take a path that, looks like that. But the work is going to be the same, and that's a very important thing. And so what that means is that f must be the gradient of some function that we're going to call g. And it turns out that this function is actually u, which is the potential energy. So therefore we can say that the work equals the integral, the line integral of f ds, which equals the integral of the gradient of the potential energy times ds, which allows us to take the integral. And what we can say is that that equals u of b minus u of a. And if we think about that in terms of potential energy, if we're going in this direction, then that equals the negative change in potential energy, which is what work equals.